Okay, let's start our lecture 17, and today we are starting with a new topic which is dynamics. So let's have the announcements. The outlines of lecture 16 and 17 are uploaded in the website like before, 16 lec.pdf and 17 lec.pdf. And like in the last class, I plan some students will come and we will have one-to-one question answer sessions. So today I request this following 6 students to come around 10:25 your local time, and then if you don't ask questions, I will ask questions. So that's the deal, right? So I think just note down ale makke failu berket kebede Bethlehem hailu David Guteta Demeke Abu Said and Deselegen Wagaso. So they will come at 10:25 in the front bench in front of the mic. So let's start with the review of our lecture 16. I have discussed about the principle of virtual work in statics. Then the relationship with the end effector moments and forces with the joint torques and forces was derived, and there we saw that how Jacobian comes into the above relation, and I have mentioned also this Jacobian which appears both in statics as well as dynamic as well as kinematics. So this Jacobian plays the dual role in statics and in velocity analysis. Then we have seen an example of two-link revolute planar arm, and I have given the assignment 4, which is to verify the Jacobian in frame 1 knowing the Jacobian in the 4th frame, and that will be due next Thursday, I believe. So let's start with today's topic. So I'll give you the definition of dynamics, then I will give the definition of inertia properties, and which are center of mass and moment of inertia of a rigid body. You remember throughout this course we are talking about the rigid body motions, which means the distance between 2 points in a body does not change as it moves. Then I will give you Euler-Lagrange definition. This is Euler-Lagrange equations of motion. We call it Euler-Lagrange formulation. This is one of the very popular formulation to write the dynamic motion of a system. But to do that, we introduce the meaning of generalized coordinates, and followed by the kinetic and potential energy of the total systems, which we will then finally used here to derive the Euler-Lagrange equations. I will take an example and give you the summary at the end. So talking about the definition of a dynamics in contrast to kinematics. So far we have studied kinematics, where we have seen that in kinematics it is a study of motions without referring to the forces or moments, whereas in case of dynamics it is the study of forces and moments causing motion. So in other words, it is a study of motion caused due to the forces and moments. So a study of motion caused by the forces and moments. Why do we study dynamics? In robotics particularly, we need to control the endpoints by moving the joints. How do we move the joints? We use actuators, say electric motors. Then if I want to use the electric motors, I should know what is the power I should choose for the motors. to calculate the power of the motors, I need to know what is the torque to be applied to achieve that motion, plus at what speed I want to rotate. So, in essence, I need to know what is the forces and torques to achieve a particular motion using a motor. So, that is for the design purpose, but for the control purpose I also need to know that to achieve a task how much torque and force should be applied, so that my computer controller can send that signal to the motor drivers. Another purpose we study is the simulation by knowing the configurations. So, if I give you a robot with certain capabilities of motors and forces to be applied by the motors, you would like to know how it will behave. So, you know whether it will satisfy your purpose or not. And then thirdly, I would like to know the reaction forces so that I can design. Let us look at my hand and I will describe these three applications of dynamics. So, this is my say robot. I want to move from point A to point B. So, to move from point A to B, having some weight maybe in my hand, then how much torque I should apply. So, A to B. So, I am moving it right from A to B, I am moving my this joint and this joint. So, how much my muscle torque to be applied, I can calculate if I know the motion as well as the properties of these links. So, that is for the control purpose, that is number 1. Number 2, I apply certain torque here, I apply certain torque here. So, where is my end effector has gone, I would like to know, that is called simulation. Okay. Then this is one link, this is another link. What is the material I should choose here? What is the material I should choose here? What should be the shape of this? What should be the shape of this? I need to know what is the force is applied on that link, what is the force applied on this link. So, if I know the reactions here and there, so I know what is the loading condition on this arm, then I can use the knowledge of mechanical engineering design which we learned in our undergraduate studies and can apply designing the robot arm. Okay. So, that is one of the topic you wanted, and I am looking for a slot when I can introduce the topic, that how a design of different links can be done. Let us go back. So, to get the dynamic equations of motions, we would like to have the mass and inertia properties of any link in that system. So, let us look at a link. So, I will do it. So, let us say this is a rigid body on the link, and we want to define the mass center of this mass center of this. So, mass center is located here, and for the calculation purposes we can use definitions where this P represents a vector of a small element here, and then this is the C, the mass center location from the origin of the fixed frame. And if I take this vector R, that means a vector from the mass center to this location here, I can define the mass center as integral P rho dV and divided over m. So, this is the theoretical definitions, but for most of our calculation purposes in this course, we will take this as a known parameter. We will take this as a known parameter. So, not too much worry as far as the numerical calculations are concerned. In practical, we have experimental methods to find out the mass center of an irregular shape object. Otherwise, if you know what is the shape, you can also use a CAD drawing. So, you can use any CAD tools to draw this body, and in the software you will have this kind of formula inside the software, which will tell you what is the mass of this body and what is the mass center, provided you specify the density or of that material. So, that is about the center of mass. Then we also define what is called as inertia matrix. This is related to mass and the geometry. So, any rigid body, depending on the shape of this body and whatever is the mass it has, we can define inertia matrix. Mathematically, inertia matrix of a rigid body is a 3 by 3 symmetric matrix. As I have written it here, it is a matrix here. Zy, Izy is actually equal to Iyz, Ixz is equal to Izx, and Iyx is equal to Ixy. This is important to remember, that inertia matrix of any body or any system. Please remember, any body or any system, okay, which is consisting of several bodies, inertia matrix for that is a symmetric. So, if I want to define formally, it is a P transpose P. P, you remember this P. What is this P? I take you to the figure again. P is the location of an elemental mass here from the origin. So, that is P. So, P transpose P, then this is an identity matrix, and minus P transpose and rho dV and V. Let me take you to the paper to show you how one would calculate. So, I have rewriting I P transpose P identity, and then this P transpose, then this rho dV. Okay. So, I calculate P transpose P, that we know if P has a component Px, Py, Pz, Px, Py, Pz, then this will be Px, Py, Pz. So, I can calculate Px square plus Py square plus Pz square, right. Identity matrix, it is a 3 by 3, which means it has a 1 0 0 0 1 0 0 0 1. Okay. Then P transpose. So, I write P first, Px, Py, Pz. I write P transpose, Px, Py, Pz. Okay. Then I perform this operation. So, Px into Px, which is Px square, Px into Py is a Px, Py, and then last is Px and Pz, Px, Pz. Okay. And then I can perform Py, Px, Py, Px, this is Py square, Py square, okay, and then this is Py, Pz, then this will be Pz, Px, okay, then I have Pz, Py, and then last is Pz square. Okay. So, now I have P transpose P is here, I have identity matrix, I have shown you how it is, P P transpose there. You can now perform these operations, which I will do in the reverse page. So, what I had is as follows. So, I write P x square plus P y square plus P z square multiplied by identity matrix, which means this will have this kind of structure P y P z square 0 0 0 P x square plus P y square plus P z square minus P P transpose, which is P x square P y P x, this is P z P x, this will be P x P y P x P z, okay. Then this is P y square, this will be P z P y, this will be P y P z P z square, okay. So, if you perform this thing, this P x square will be, so P z square, this will be minus P y P x, this will be minus P z P x, this will be minus P x P y, this will be P x square plus P z square, because this P y and this P y will cancel out, this will be minus P z P y, this will be minus P x P z, this will be minus P y P z, and this will be P x square plus P y square. Now, if you look at the expression in the previous page, just let me show you for a while. This rho dV integral over V will give you the element. So, let us integrate. So, integration over this rho dV integration over V will give you the first element of this inertia matrix, which is called Ixx. You integrate over this rho dV over V, this will give you Ixy. I integrate here rho dV. Now, you will see these two are same. So, even though I write Yx, but that is equal to Ixy. So, this is the way the I matrix can be calculated mathematically, okay. But as I told you, for our numerical example purposes, okay, we will be provided by these values, okay. We are not going to calculate these values from the material shape or material mass. I have just shown you to explain how they are calculated from, let us say, when a software calculates it, how it calculates, they calculate in this manner. This is just for your knowledge, which you have studied in your undergraduate mechanics course. We go back to the slide. So, what you see is Ixx here is the one which I have told you, which is integral over within bracket Py square plus Pz square rho dV, okay. These two are equal, this and this are equal, this and these are equal, and then this is the diagonal, I think. So, if you remember from your undergraduate studies, these are called the principal moment of inertias, no. These are called the moment of inertia, and these are called the product of inertia, okay. This one is called the product of inertia, and diagonal one is called the moment of inertia. Suppose if you have a matrix I with only diagonal elements, all others are 0, then those moment of inertia we call it a principal moment of inertia. I repeat, when this I matrix has cross terms like this, which are called product of inertia, these terms are called moment of inertia. But if there is a matrix where you have only these are non-zero and this is 0, this is 0, this is 0, this is 0, this is 0 and this is 0, then this moment of inertia becomes principal moment of inertia. Okay? And we have used similar techniques to find out the stresses. This is an inertia. Similar concept is used as a stress inertia, which we have used using Mohr circle in our strength of material classes in our undergraduate studies. Here it is a similar concept. Anyway, so as I say, Ixx etc. are the moments of inertia. So, in a rigid body, to study the dynamics, we need following important characteristic. One is mass, one is mass center location, and we also need the inertia, but inertia about certain points. This is inertia about the mass center location. Please remember, what I have calculated is the inertia about mass center. So, three things: mass, mass center location, moment of inertia about mass center. To understand little bit of the physics part of it, that where mass comes into picture, where moment of inertia comes into picture. So, to look that, I have pointed out three items on this slide, that how mass and moment of inertia are kind of playing important role. First, moment of inertia of an object is a property of what? Mass and the geometric shape. Okay. So, mass and geometric shape both are important property which reflects in the value of moment of inertia, and later we will see that this influence the rotational motion, okay, which I am writing at the end here. Okay. Let us go to the next point. Mass influences a linear motion. Okay. When a body is moving, it has two combined motion. One is a translational motion, one is a rotational motion. Suppose if a body is moving in a straight line, look at my hand. If a body is moving in a straight line, then we can apply the Newton's second law, that mass into acceleration is the force applied. So, you see moment of inertia is not coming into picture. If I have a pure rotation, then it is inertia into angular accelerations. So, inertia is coming into picture, and if you remember the formula for inertia about z, it is something like mass into length square or diameter square of the object you are discussing with. So, mass influences the linear motion only. The mass affects the rotational motion indirectly, as you see in the slide. So, you will be able to see in the slide. So, mass affects the rotational motion indirectly. Why indirectly? Because mass is used to define moment of inertia, and moment of inertia affects the rotational motion. So, that is why we write mass affects the rotational motion indirectly through, as I wrote here, through moment of inertia. Okay. So, the role of mass and moment of inertia is given, and hopefully it is clear to you. These are preliminary just definitions I have given you now, inertia properties and how much. Now we come for the formulation to obtain dynamic equation of motion. So we write d dt of del L del qi dot minus del L del qi is equal to phi I. Let me define each term one at a time. This L is called Lagrangian, okay, it is a scalar quantity. So L is called Lagrangian. Basically it is an energy, kinetic energy minus potential energy, okay. So here I write kinetic energy minus potential energy, no problem, we have studied this thing earlier. Qi is called the generalized coordinate, okay, it is a generalized coordinate, and phi I is called generalized force. Let me spend some time to explain you what is the meaning of generalized coordinate using these papers. Okay. So let us look at the paper. Suppose I have a link. Suppose if I have a link of some shape. If I want to find out its motion, I know that this requires 3 coordinates. So it requires 3 coordinates. Which are the coordinates? Maybe x and y. Let us say this is capital X, this is capital Y, so small y, and this angle is theta, or let us say phi, no sorry, let us say psi. So 3 coordinates could be x, y and psi, okay. So this we can call it a generalized coordinates, okay. Generalized coordinate means any coordinates is a generalized coordinates, and generalized coordinates are required to specify the configuration of a body or system, okay. So we need x and xy. One can also define say this is x1, this is y1, this is x2, this is y2. So I can also define the above using 4 coordinates also. So the 4 coordinates x1, y1, x2, y2. So when I use these 4 coordinates, I can still define the same motion wherever it goes. I can still define x1, y1, x2, y2. So I can use this set also. I can use this set plus this set, no problem. So I can also use 4 plus 3, 7 coordinates. Okay, I can define 7 coordinates. So as long as it defines its configuration, this is a generalized coordinate, okay. Now You may say so that I want to use the polar coordinate. So far I have given you Cartesian coordinate. One can use a polar coordinate. In polar coordinate we talk about r and theta. So, you can talk about r1 and then this will be r2 and then the angle. So, I use a different color. One can use r1, r2 and theta as polar coordinates to define configuration. So, this is also generalized coordinate. So, generalized coordinate. So, any coordinates which will define the system completely are generalized coordinates. Now, the question is whether there is independent and dependent. There are two things comes into picture. In this example, if I have used three coordinates, they are the minimum number. This is minimum because I know the system has 3 degree of freedom. Okay, 3 degree of freedom. So, they are minimum, but here I have used 4, they are not minimum. So, minimum are 3, but then how are they related? Okay. For this thing we go back to one of our very first few classes, the concept that degree of freedom is equal to number of generalized coordinates minus number of independent constraints. Okay. So, if I draw this picture again for you, so this is x1, this is y1, this is x2, this is y2. Think carefully. If I specify this, can I specify arbitrarily this one? I repeat, x1, x2, y1 given. Can you arbitrarily, I am writing in capital, arbitrarily decide y2? The answer is no. No, because y2 can be calculated as x2 minus x1 square plus y2 minus y1 square is the length. This has a length a, it will be a square. So, you can calculate y2 from here, y1 plus square root of a square minus x2 minus x1 square. So, you cannot specify now because y2 has to obey this formula. Y2 has to obey this formula. Okay. So, here we have 4 and the constraint. So, this is a constraint here. The constraint is the position of these 2 points should be such that this distance square plus this distance square should be the length square. This we know, Pythagoras theorem, right. So, Here I have one constraint, so there is a one constraint, so I get degree of freedom is 3. This is always true. Degree of freedom is equal to number of generalized coordinates minus number of independent constraints is equal to the degree of freedom. So, it is 3. Let us proceed with the same example, but change the system little bit. Now, I put a hinge here. Let us put a hinge here. Okay. I change the color. I put a hinge. So, if I put a hinge here, and then if I want to use, say, for rigid body, I know I need 3 coordinates. So, if I use these coordinates here, let us change to a different page. So, I have this system here and I put a hinge now. So, I am using, now let us say I put my coordinate from here x, y, and now I want to use this x, y and this angle theta. So, x, y and theta are generalized coordinate. For this system, we know it has 1 degree of freedom. It has a, we know it has a 1 degree of freedom, which means it should have 2 constraints. It should have 2 constraints. What are the 2 constraints? 2 constraints are the pin joint here does not allow this point to move in this direction, does not allow to move along x, does not allow to move in y direction. How do you express in terms of equation? In terms of equation, x is equal to a cos theta. So, this is my a, y is equal to a sin theta. So, I have chosen 3 generalized coordinates, out of which 2 are constraints. So, obviously, you have 1 degree of freedom, 3. So, this is 3 generalized coordinates. So, 3 minus 2 is 1 degree of freedom. So, alternatively, I know that it has a 1 degree of freedom, only one coordinate will be sufficient to describe. So, I say I will use theta to describe its motion. So, this is a generalized coordinates, this is also generalized coordinate, because this generalized coordinate is sufficient to describe its motion, but since this is equal to the minimum number, so we call it independent, and this becomes dependent. Okay. So, this is independent generalized coordinates. Okay. So, this is the concept of coordinate, number of parameters used to describe the system completely, be it a Cartesian coordinate, be it a rotational coordinates, or be it a polar coordinate. Any coordinates which will be sufficient to describe it's a generalized coordinates. If we use more coordinates than required, we call it a dependent generalized coordinate. If it is like this, which is equal to the number of minimum, then we call it a independent generalized coordinates. Okay. Now, in parallel to the definition of generalized coordinates, we can also define generalized force. So, we have now generalized force. Let us go back to the old example here. Okay. So, if I use this set x, y and psi for the body which is moving in a plane anywhere. Okay. So, to move along x directions, I need certain force, that is Fx. To move along y directions, I need certain force, that is Fy. To rotate this body, I need certain torque. So, anything, if I want to get a displacement x, who causes this displacement? This is say Fx. Who causes this displacement? Fy. Who causes this displacement? This is say moment about z. So, these three becomes a generalized force correspond to the generalized displacement x, y and psi. Come here, if I use 4 coordinates to describe it, so I need a force to move this point along these directions. So, this is a force required Fx1. To move this point along these directions, I need a force Fy1. To move this point in these directions, I need a force Fx2. To move this thing along, x and y, I need Fy2. So, according to the generalized coordinates you are choosing, corresponding force to achieve that displacement is called the generalized force. So, now coming to that hinge example, here if I choose this theta as my generalized coordinate, who will cause this theta? Who causes this theta? A rotational torque can cause this thing. So, corresponding to this thing, I can have a tau as a generalized force. So, generalized force, the force causing generalized displacement. Okay. So, in the Euler-Lagrange equations which you have seen on the screen, that is d dt of del L del q I dot minus del L del q I is equal to phi I. So, according to that notation, this could be q1, this could be q2, this could be q3, okay. And then this is one set. In a separate alternative way, this is just q1 and this will be phi 1. So, this is this is this, okay. For this one, if we want to define corresponding force which will cause maybe Fx, which is equivalent to phi 1, it is Fy which is equivalent to phi 2, and then this one is equivalent to say Nz equivalent to phi 3. So, in the Euler-Lagrange descriptions, now we can go back to the screen. So, in Euler-Lagrange descriptions, meaning of q1, q2, q3, meaning these are generalized displacement and phi I is a generalized force. Q I dot means the time derivative of the generalized coordinate, and this is just the force. So, if you want to write the kinetic energy and the potential energy, what we do is we write the kinetic energy of one body, say ith body. We can calculate the kinetic energy of ith body by calculating the mass of its and the velocity square, in other words velocity vector transpose velocity. Here velocity I mean the mass center velocity, plus this is for your linear kinetic energy, and now then we calculate the rotational kinetic energy, which is equal to the angular velocity transpose the inertia matrix, and this is again angular velocity. So, this you have to remember, or you have to consult a book every time you solve a question, and once you keep doing it, it will be in your memory for the duration of the course. So, once I calculate the kinetic energy for the ith body, I can calculate for all the bodies by summing over it from I to n. Notice here I am calculating the kinetic energy from the mass center velocities. So, these are Cartesian velocities. So, this is one set of generalized coordinates. If I choose a different set of generalized coordinates, I need a relation between this one and the generalized, which we will see through examples. Next, if you want to calculate the potential energy, we can calculate, we know mass into g is the weight, and at what height, that is Ci transpose, that means assuming that it is perpendicular. So, C it is a projections of mass center along the g will give you the potential energy, which is very similar to what we learned in our earlier classes, undergraduate classes, called mgh, mass into acceleration due to gravity into height. Here that height thing comes from this transpose, Ci transpose g will give you the gh term, and the negative we have done it because we are assuming the gravity is acting on the negative of the z. So, we are writing as a negative one. So, this example, I think there is no more time today. So, this is one example for 1 degree of freedom system, which we will do it in the next class, but today we will stop here, and if there is a quick question from the audience, I will take it. Otherwise, these 6 students will come with their questions, or if they do not have a questions, I will ask 1 or 2 simple questions to be answered. So, I will wait about 20 seconds if there is any general questions before I request all 6 to come front. Any questions from today's lecture? Okay, if there is no question, can I request these 6 students whose names would be appearing in this slide? Alimakef Hailu, Bereket Kebede, Bethlehem Hailu, David Gudeta, Demeke Abu Said, Desalegen Ogaso. So, others can leave if you want to, or you can watch them how I am asking them questions, but I would request 6 students to come in the front of the mic, please. Come in the front bench. All 6 are here. How many are absent? Can somebody respond who are absent? I can't see you on the left. That means in your right. Alemakhev, please raise your hand. Alemakhev Hailu, raise your hand. He is
absent, sir.
Okay. Bereket Kebede, raise your hand. Also absent?
Absent, yeah.
Okay. Bethlehem Hailu, raise your hand. Okay, thank you. David Gudeta, raise your hand. You come next to the lady, next to her left. Yeah, good. Then Demeke Abu Said, come next to him. I can't see your face. Come next to him. Left to David. Okay. Please come. I can't see you. Demeke. Atto Demeke. Hello. Can you hear me? Yeah. Demeke, please come in the middle.
He is absent.
Okay. And Desalegen Ogaso? Okay. So only 3. Okay. So have you done your assignment 3? The last assignment which I saw?
Yes.
Okay. Do you have any special questions to ask me? Otherwise, I will ask you.
Ask us. We don't have any question.
Okay. Tell me why this Jacobian coming into statics has a different form than in the velocity. I give you 20 seconds time. First, Desalegen to answer. Let me share a concept with you which I play here. Maybe it is in the same line in the long distance mode. I have something called question of the day, right? So these 6 students whom I am calling, they should be able to ask a questions based on the last class given. You can create any questions, okay, based on the last 1 or 2 classes, and you should be asking me these questions, okay. If you don't ask the questions, then in the next class you have to ask 2 more questions, okay. And of course here, if the student do not ask in the second class, they get no attendance. But here I will request Professor Tafese to mark you absent on that day. No? So first day, every day you should come prepared with the questions, and those 6 students whom I call should be asking the questions. If you don't ask any questions, I will ask you to ask the question of the day, and if you are not able to ask, it will be next class 2 questions. If you are not asking 2 questions in the second day, you will be marked absent, okay. So Jacobian answer, anybody has the answer?
Yes.
Okay, tell me.
To determine the Jacobian matrix
Okay.
in statics, we are considering regarding the first frame.
Okay, then velocity?
Velocity up to index vector.
It's the other way around. Okay, for the statics, when we do the statics, the force which we are measuring in the end effector frame, and when we calculate the velocity, it is in the base frame. So that's why the accompanied Jacobian structure looks different. To show they are same, we have done that exercise of pre-multiplying the orientation matrix, for which you will be doing the assignments also. Okay, is that clear?
Okay.
Okay, so thank you. Next time please come prepared with the question of the day, okay, and let me say goodbye.
Goodbye.